But the thing is, the model is a reflection of the user. There's a great example in chess play. So because these models learn the statistical distribution of chess moves, if you play smart chess moves, the model will actually play like a smart chess player. And if you play dumb chess moves, the model will play like a dumb chess player. It's the same thing with coding. If you ask the wrong questions, if you write crap code and you get it to complete the code, or if you do anything stupid, the model will be stupid because the model is a reflection of you.
This is just a mathematical fact. If you don't like it, I'm sorry. I'm sorry you don't like it, but it's just a mathematical fact, okay? The whole crux of Turing machines is that they are allowed to, at runtime, have an unbounded, so a potentially infinite amount of compute. We don't fix it ahead of time. We don't say you get to run for, 82 steps and then I terminate you.
Today is an interesting episode. It's just the two co-hosts of MLST having a chat about the new models from OpenAI, about test time inference, about reasoning. And if you hang around to the end, or maybe you can just skip to it if you want to see that, we actually test out all of the LLMs on a very interesting brain teaser from Duggar's early years at MIT. And we also show a little bit of us playing with some code in Cursor. And I don't think we've ever shown us writing any code or doing anything like that ever before on MLST, so it's a bit interesting. Anyway, I hope you enjoy the show. Any thoughts, Duggar? Why should people watch this show?
Well, I mean, people should watch this show because I think you and I are maybe, we try to offer like a bit of a more critical perspective on OpenAI. So we've been through a couple hype cycles and we try to be a little bit more grounded in what to expect. So people should watch it to get probably a different opinion from the bulk of opinions they're getting right now, and some food for thought, and maybe also just what to watch out for when they're using these tools themselves. So when we talk about things like the computational classes, and I'm going to rant here for a second and say again that many of the things in theory of computation, in my educated opinion, really sit on the cognitive horizon of the vast majority of even smart people. Okay, like I and many other smart people have said theory of computation is a class that blew their mind. And, Turing was a genius, beyond geniuses, because he invented this field, really. Okay. And so those things, like these critical points that are made there, like the difference between computational classes, and folks, these are not related to complexity classes. Don't get confused. Okay, MP complete, blah, blah, blah. None of that has anything to do with what I'm talking about. I'm talking about Turing machine versus push-down automata versus finite state automata, etc. These are not trivial in the slightest. They are not technicalities. They are extremely powerful and vital and important fundamental concepts of computation.
The Brave Search API brings affordable developer access to an independent index of over 20 billion web pages, powered by real anonymized human page visits to filter out data and refreshed daily with tens of millions of new pages. We'll get started with 2,000 free queries monthly at brave.com/API. Okay, but we're still arguing in the regime of there is a space of effective computation which is not reachable, and it would be useful if we could reach them. Mm-hmm. Let's go back to the conversation with Schmidhuber. Now, he was making the argument, as many do, that it doesn't matter if you have a finite amount of computation because the universe is finite, everything is finite, we can just build bigger things. And a lot of this comes down to your opinions about infinity, and you can bring in like the decidability and the halting problem as well. But explain why is this important?
Well, I mean, and this is like kind of a similar comment that J. Mark Bishop made on LinkedIn, right? When we posted, it was probably that video or something about Turing machines a while back. And he said, "Oh yeah, but I can build anything out of NAND gates, and so therefore I can build anything out of neurons, including like the computer." That said, these people should know better. Like, they honestly should know better, because they should remember they should remember the days. I'm even young enough or old enough to remember, let's say, the days when computers literally had tapes, okay, where you would build a computer and you would program a computer, and that computer is a finite thing, okay? It sits there in a room. It's got like a fixed number of vacuum tubes or transistors or whatever the hell, okay? It's a finite volume, finite mass thing sitting in a room, okay? It's clearly a finite entity, as like all computers are. But these computers had a tape deck, okay? And that tape deck was like the tape from the Turing machines, and it was a read-write working memory. So the computer could sit there and turn the wheels of the tape, right? Backwards and forwards, and go along and write stuff and read stuff. And guess what? It could run out of memory and a little light would turn on, okay? Or a little counter, which would say, insert another tape. And you take off the tape and you set it in a box, and you go over to your box of empty tapes or tapes you don't care if they get overwritten, and you put it on there. And the compute continues. You don't need to reprogram the machine. You don't need to rebuild it. You don't have to retrain it like you would have to do with a neural network. That program is constructed such that it will just continue the computation. And this can go on forever. Like the machine can keep telling you, add next tape, add previous tape, add next tape, add previous tape, add previous tape, add previous tape, insert previous tape, right? And you just go back and forth forever, like for some unknown amount of time. And if you run out of tapes in the room, well, you drive over to the warehouse and you grab another box. And if you run out of tapes in the warehouse, you go to the factory and you build some more. The point is, all during this time, you never had to reprogram the machine. Neural networks are like when we train neural networks, when we train them, and it's critical, it's not just the neural network, it's neural network plus the procedures we use to train it, okay? They learn algorithms that don't know how to do that. They don't know how to do that. They can't tell you, I've run out of memory during inference time, I need you to add more. And then you add more and it does something. It says, I've run out, give me another tape. We don't know how to train algorithms that know how to use an expandable, a potentially infinite amount of memory. This is the critical difference, and those guys should know better. They should know better.
Okay, but so Turing machines suffer from this decidability problem, right? They could run forever, but you're saying there is a class of programs they can run because, of course, the program stays the same. We can just expand the memory,
right?
And many of these programs, if we look at the class of useful programs that we might want to do here on Earth, they could still be represented with a very large finite amount of computation in a neural network. So the argument is basically for a large class of useful problems, we can use neural networks. What is the main argument why we need to have this different mode of computation?
Well, I would first say, the world's already run into plenty of problems that require Turing machines and require memory. Like this thing about insert tape and whatever, it's a real phenomenon, right? Like adding more nodes, adding more storage, and you don't have to reprogram the machine. And we have many theoretical results about problems we care about that require Turing machines. They require Turing machines in the sense that, when some input comes in, and it can be some finite input, by the way, some finite input is given to the machine. The amount of time and storage that it needs to compute the answer to the problem that we care about is a variable. And it's a variable that depends on the input. And in fact, it's a variable that we may not even know ahead of time, right? So there's a large class of things that do this. So no matter how big you make your neural network, it's always going to be the case that you can run into a problem a problem you care about, okay, that neural network just isn't going to be able to solve because it doesn't have enough, memory, basically. And people say, oh, it doesn't matter, we'll just build them like Huge. We'll make them huge, man, like super massive, the size of the entire state of California. And then at that point, like it'll be able to solve like every problem human beings will ever care about. Okay, maybe you can, maybe, but it's pretty unlikely because these problems, right? When you try to take a Turing machine program, one that has like a variable amount of sort of compute space and stuff like that, and you try to instead convert it into like a single forward pass sort of neural network that doesn't understand iteration and read-write memory and things like that, what happens is you get this kind of exponential blow up of the size of the program. And this is like nothing new, folks. Like, again, people should know, like computer scientists should know this. I'll give you a perfect example. Okay, in your computer chip today, your CPU, whatever it is, I know you're always bleeding edge max, so it's probably like M3 or something. You probably have special access to it. But like in that chip, things like, say, multiplication of numbers. Well, you can build a very simple circuit that can sit there and read and write to memory and do multiplication, but it'll take a while. Like it'll take, whatever, in steps or something. Instead, you can blow up the size of the circuit, make the circuit, say, quadratically larger or exponentially larger, and then do the multiplication in like maybe even one step. All right? And we do these kind of trade-offs. Like we do them because something like multiplication you care a lot about. And so you build a chip that has a very large circuit and you solve for what's called its timing closure so that you can still calculate the multiplication and like a very small number, maybe even one if you can get there fast, passes through the chip in a certain amount of time. Okay, but it requires like much, much larger, circuits. And especially the types of like complex reasoning that we really think about when we talk about reasoning, solving difficult scientific problems or brain teasers or complex logic problems or whatever, usually fall into the category of things that require this type of like iterative Turing type of computation, right? Just because things like, logic is Turing complete and lambda calculus and et cetera. So you end up there. Like you end up needing, Turing machines. But that doesn't mean all useful things need that. So I have a lot of sympathy for somebody who argues there's value in finite but structured computations and things that are structured in a way that are very similar to the problem. So like if you could imagine if we were doing some type of three-dimensional problem solving, it might be cool if we had memory architectures which were actually three-dimensionally wired and somehow like, yeah, cool. Like, I mean, I'm sure that all that kind of stuff is very cool.
Let's just start with your definition of reasoning. What is it for you?
Well, so I will give that. Before I give that, I understand the word is used to mean, lots of different things, okay? But if you literally just go and look in the dictionary or the wiki or whatever, you're going to see that almost all of those kind of common sense definitions, okay, they have two components in common. One is that they all refer to a process. A process. Okay, so we have to think about kind of iteration that kind of unfolds here, a process. And then the other thing is it's a process that applies logic, okay, and sort of rational, sets of rules. Okay, so to me, the most, general process that applies logic is an effective computation. In other words, it's the computations that Turing machines can perform. That's another word for all the possible computations that Turing machines can do is effective computation. I can't really tell you why it's called effective. Okay, that's just the name for it. So to me, reasoning is an effective computation in pursuit of a goal or inference of knowledge.
Okay, but many of the computations that neural networks do, of course, are a subclass of the types of computation you can do on a Turing machine. So they are still effective computations, and they are, in many cases, still in pursuit of deriving knowledge or achieving a goal. So why is that not reasoning?
Well, so I can't disagree with that. Okay, it's and I would say these people are kind of like being the technical, the kind of arguing technical points, but kind of missing the forest for the trees. It's like, sure, the soda vending machine, okay, at the gym, you probably shouldn't be buying soda if you're at the gym, but the drink vending machine at the gym, okay, is performing a subclass of effective computations, namely it's a finite state automata, and with the goal of collecting money and dispensing a drink. Is that reasoning? I mean,
this is the problem, right? Because what we don't want is an anything goes definition of reasoning, right? So I said reasoning is knowledge acquisition. The new OpenAI models don't reason, they simply memorize reasoning trajectories gifted from humans. Now is the best time to spot this, as over time it'll become more indistinguishable as the gap shrinks, which is to say the knowledge gap. For example, a clever human might know that a particular mathematical problem requires use of symmetry to solve. The OpenAI model might not know this yet because it's not seen it before in that situation. When a human hints the model and tells it the answer, its chain of thought model will be updated, and the next time in a similar situation it will know what strategy to take, and this will rinse and repeat as they sponge reasoning data from users until many of the holes in the Swiss cheese are filled up. But at the end of the day, this isn't reasoning. It's still cool though, I said. Now, this is the interesting thing, right? So a lot of reasoning is just kind of knowing what to do. Because I know you're saying it's an effective computation. Some of the people responded to this saying, oh, Tim, what are you talking about? Reasoning is just mapping an input to an output in data space. But Walid Sabo would talk about this hierarchy between data, information, and knowledge, right? There's a relationship between knowledge and reasoning. Reasoning is all about, this is what I know about the world, and I need to perform a computation. And in order to do so, I need to basically make a new model to understand some effective model, right, to do the thing I need to do. So I'm going to be composing those models together. I've created a new model, and then I perform this effective computation. That's what reasoning is, because there are many problems that are quite binary. So if there's A, B, and C, and in order to understand C, I need to understand A and B. I need to know about A and B, right? If I don't know about A and B, I can't do C. So in the absence of A and B, I can't actually solve that problem.
I agree, and there's. So I would say that the drink machine, is not performing reasoning, okay? Or if we really have to be, technical about it, it's performing reasoning at level, 0.0, something another, okay? And then an effective computation that sits there and does, let's say, some geometry calculations and some world modeling and some image recognition and some other Turing complete, computations that may not halt and whatever, then that's doing reasoning at, level 0.8 something another. I mean, we could have a whole scale here if we needed to, right? But if we're just going to kind of break things down into some binary, the soda machine's not reasoning, and neither is a dictionary. Okay, if I go and I look up my problem in a massive dictionary and it has the answer and I spit it out, that's not reasoning. It's not performing the computation that led from the problem to the result. It's just doing a lookup. And I mean, so now we switch from say the DeepMind paper we were initially talking about to o1, right? And I think it's kind of important to emphasize what you said about what o1 is doing and how it was trained, right? Which is when they trained it, they took a whole bunch of problems, ran a bunch of, passes in very creative mode. So like temperature 1 or whatever, where it could kind of come up with, all kinds of fantasies about justifications for an answer. And then they selected those which had the correct answer. Okay, so we've got all these trajectories of reasoning. And by the way, those were all, by some definition, reasoning. Lots of them were complete nonsense and led to the wrong answer. Okay, so then they selected those which gave the right answers, and then used those to retrain the model so it was more likely to give patterns of quote reasoning that gave right answers. And so, like you said, it's sort of building up this dictionary of kind of specific rationales. Let's call them rationales. It's building up like a massive database of rationales. Okay, here was a problem, here was my rationale, it gave the right answer. This massive database of kind of little rationales. And then when you give it a new problem, it sort of does this context-sensitive hashing and matches the rationale that's kind of closest to it, and then sort of fills in the blanks like an ad lib, sort of let me just stick in all the stuff in there, and then hopefully it works. Well, sometimes it works, sometimes it gives complete nonsense. And is that reasoning? Not in my opinion. This is not what we're talking about when we talk about reasoning. We're talking more about the application of a set of first principles to some inputs in a process of applying logic to derive the answer, right?
Yeah. And to be a bit more specific, just in case the folks haven't played around with this yet, it's doing the generation of chain of thought templates. And for those that don't know about chain of thought, it's a type of in-context learning. So a lot of models sometimes do better, or they generalize better and the original version of this, I think, was called Scratchpad, where you break down a problem. It might be addition or multiplication, and you kind of say, you need to do this, and then you need to do this, you need to think about this. So it's kind of decomposing a problem into a rationale that could be applied in many future situations. So you kind of say to the model, think out loud, or apply this thinking protocol to it, and then the model works better. But the thing is, with prompt engineering and chain of thought, the human supervisor always had to put this into the model. So what they did was they came up with quite a clever idea. They said, well, why don't we get the model to prompt itself with chain of thought, right? So what they've done is, and as I understand, I'm just guessing what their architecture here, I think it's really simple. I think that you have the base model, which is just trained to match the statistical distribution of text. It's just basically a autocomplete. And then they do this next thing called RLHF, which is where they basically shape the distribution by supervising it with examples of conversation trajectories that are good. So saying this is good, this is bad. So, go here, don't go there. I think all they've done is the same thing with chain of thought trajectories. Now, of course, the question is, well, where did they get the chain of thought trajectories? I'm guessing that they've done a bunch of synthesized data, and they've hired a whole load of people to reflect on what these cognitive templates are. They've done RLHF. And the interesting thing is, this is all in one model. Now, it gets a bit more complicated than that. So the model has a mode. A lot of people, my original intuition was that there was more than one model. There was like an adversarial chain of thought model, which was injecting prompts and doing this big search. I don't think it's that. It's really simple. So very similar to how RAG models go into a different mode. So when they detect that this is a RAG type query, they go into a different mode and they start self-prompting themselves in a very specific way, which increases their faithfulness. It's a similar thing with this. So it goes into a thinking mode. It starts generating these chains of thought, and they hide the chain of thought, but it's all going into the shared, in the context for this one model. And the UI is quite interesting because it says, I'm thinking about this, I'm checking the policies, like I'm checking this, I'm refactoring the answer, I'm doing this, and then it just gives you the result. And I think that's how it works. So it's really simple.
Yeah, well, it's
in a way.
Well, we don't know because they don't exactly. OpenAI isn't exactly that open about what they're doing behind the scenes and how things function. It's almost like there's a missing symbol in front of the company name, which is like the not symbol, the tilde or an exclamation point or something, like not OpenAI. So I don't know. I'm going by blogs and whatever else they've kind of published on the site. So I think it's something along those lines. And it's kind of like, of course, it's more the same. You and I have talked about this so much on the show, this idea that really, neural networks are doing this kind of interpolation, this sort of locality sensitive lookup tables, and they've just gotten so massive now. They have these massive tables of lookups that they can do, and then if at runtime you're kind of allowing it to do that a few thousand or hundreds of times or whatever over some period of time, and then kind of selecting the best one, like you were doing a lot early on, when you and I were using GPT for programming and whatnot, right? Where you would ask it to generate something, you would kind of give it back to it and said, this is pretty buggy, see if you can fix it, and you kind of iterate with it, right? Like really just kind of in a loop, and then after a certain number of iterations, it would kind of improve itself. So I don't know why people get so excited about this kind of stuff. It's in the long term, folks. This is not the path to AGI. Okay,
Sure, but a couple of things on that. First of all, you were talking about the supervision. So when you talk with a language model, you're generating some code. The problem is actually quite ambiguous and poorly specified, because in code,
well, can I just interject really quickly there and just say that that can be self-supervision, or in other words, you can set up a system where you just ask a large language model for some code, and you've decided ahead of time you're going to feed it back to itself 5 times, each time telling it it's buggy, try to improve it, right? So there doesn't necessarily have to be any human supervision. It can be a kind of iterative, self-supervised, finite thing, right?
Oh, we can, but my point is that never works well. So the reason why language models work so well for generating code is it is a didactic exchange of knowledge discovery, right? So I tell it to do something, usually it gets it wrong, and I say, no, I actually wanted this, and then it might come back with something interesting, and I'll say, no, you've just accidentally deleted a load of my code, but I quite like this thing. Why don't you keep that thing, but go back to that thing? Like, the biggest problem with Gen AI coding, by the way, is it constantly violates the golden rule, which is if it ain't broke, don't fix it. It always wants to delete loads of stuff that it thinks isn't important because it doesn't know all the assumptions and the reason why it was there in the first place, and then it doesn't do the thing you want. So anyway, the reason why having this tight supervision process is important is because the model will diverge. So having a reasoning system that actually goes many, many steps, and what about this, and what about this, and what about this, it's actually not that useful. Right, because it's going to be wasting loads of cycles, which you're paying for, by the way, doing things that you didn't even want it to do in the first place.
I can't go that far. I agree with you that it's very inefficient. I agree with you that it's very inefficient. But I think if we really knew how to train neural networks so that we could train them train them knowing that they're going to run for some, unknown. It has to be unknown, some unbounded amount of time, and kind of looking for a stopping condition. Once we get to that point, I think the training process can kind of grind away some of that efficiency. I think what's happening right now, though, is, as far as I can tell, but again, OpenAI is not that open, is that when people are using these things, what they're doing is really the stochastic gradient, optimization is done, and then it's over with, and then they take that thing and they try to hack it to do this iterative work in a variety of kind of hacked ways. Probably because if you actually tried to train it to do this, inference time, or to train it under the conditions that it would be doing this inference time iteration, then it becomes too difficult to train, right? And so we're stuck in this situation. And so that's probably a lot of the blame for this very real inefficiency that you're talking about, I think.
Right. I mean, another interesting thing is that because it's all in one model, the models actually really struggle in this autonomous setting, and they really struggle with complexity and depth. So if you took Claude 3.5 and you told it to be like, o1-preview, right? You said, I want you to generate all of this chain of thought, and I want you to, the tree needs to be depth 10, and I want you to just keep going and keep going. It won't do it. And part of that is because these earlier versions of the models were trained to be concise, right? They've had this RLHF done to them. They don't want to be verbose and they don't want to do it. But even if they were verbose, they would actually kind of collapse under their own weight because of the complexity of this tree going up.
Well, I'm gonna have to take your word for that, because I don't know that that's the case, but I would not doubt that in the slightest. And believe it or not, like, this may sound kind of nutty, possibly, I'm not sure, but to me this relates to the points that Stephen Wolfram makes, right? Which in his let's say universe of thought, right? You have computations that really they're either in the category of they sort of do nothing. They're just like super simple ordered. They draw like a straight line, okay? Or they do total just noise. They just generate, noise. Or they're on this kind of like chaotic boundary, right? Where they do interesting things, the kinds of computation that do interesting things. And those interesting things can exhibit like, irreducible behavior and the most kind of complex behavior that we're really interested in. And I think that stuff like general intelligence and, the hardest problems, they sit in these very chaotic kinds of zones. And so as you start to take a computational machine and you push it closer and closer to that greatest of capability, it becomes like a nightmare to train and operate, and it's sitting on this boundary where it can easily fall off into either total nonsense or flatline, right? Like, it's almost like you've configured Claude to fly too close to the sun, and it got too close to what's required for general intelligence, and then it just flatlines, and it starts repeating to itself like, I'm bored over and over again, or just outputs total gibberish like, the strength of the Wi-Fi signal indicates that he was farting throughout the entire dinner, and you're like, what? Like, that's probably what's happening.
Yes. Well, that leads me on to the next thing, which is that there is an interesting kind of mode collapse. So because they have, and I'm assuming that this is what they've done, they have got a combined model, which is both a chain of thought reflective prompter and a standard language model. It gets kind of stuck between the two modes, and the modes interfere with each other. Now, of course, if I was designing this thing, I would have had a separate chain of thought reflector, and I would have had them kind of interact with each other in an adversarial way, maybe even in a multi-agent way. They probably do that during training, but not during inference. But anyway, my point is that the o1-preview and o1-mini, they're very good from the first shot. So you give them a problem, you don't need to specify it very much, and o1-mini in particular for coding is incredibly verbose. It will, it'll generate a whole bunch of COT trajectories, and then it will give you loads and loads of code. I think it's been designed for coding because it just gives you an insane amount of code. And then you refine it and you say, okay, well, actually, I want to move on to this other adjacent problem now. And it basically mode collapses. It's completely useless. Not completely useless, but useless in many cases. And it's because in its context, there's all of this COT data, right? This chain of thought data, and that actually interferes with the new thing you want to do. Now, with something like Claude 3.5 Sonnet, that doesn't happen. It's got a 200k context. You can just continue onto a new problem and a new problem, and if anything, it helps you having all of this stuff in context because it's all contextual information. It knows what the assumptions were. It knows why you did things, and it just continues on, and it's incredibly reliable. With the new GPT models, you actually need to basically start a new session. And in many cases as well, if you're using something like Cursor, it's got an apply model. So it runs another model just to apply your edits to the code. And that's currently broken. Well, I say broken, it doesn't work very well on the new models. But what I've found myself doing is I start with o1-preview, and it will say something interesting, and then I'll switch over to Claude and I'll go on from there. It's not possible to continue. In the real world, we are dealing with ambiguity all the time, and we do a lot of creative thinking and so on. And it is it's like a symphony. It's a dance, right? You're dancing with a language model. You're sharing information. You're updating your models. And you need to be supervising this thing every single step of the way. How many problems are there really where you can just say to a model, look, go and do me this, go and do this thing. Here's some software. These are the requirements. It needs to do X, Y, and Z. Just go away and create it for me. There's an infinite number of possible software programs that you could write that fit this set of requirements. How on earth is it going to write the correct program? It's not.
Yeah. Well, I mean, and then you start to ask, okay, well, somebody's going to argue, no, it is correct because it met all the requirements, and you're like, okay, sure. But then as soon as we added this other, pretty reasonable use case, it just like totally broke down and has to be, recoded because it's not following any kind of, general principles. I mean, a lot of this is sort of like this philosophical debate, right? Which is if you're trying to walk across town and get from the bar where you were just, drinking too much, back home, okay? If 10,000 drunks perform a drunkard's random walk, some of them will make it home, okay? Most of them won't. Would you say that the ones who made it home were reasoning and they, were reasoning their path home? Like, no. I mean, it's just by chance some of them made there. So anytime where you've set up a problem wherein it's very easy to check if you have the right solution, of course you can randomly generate solutions, and if you generate enough of them and you can check if it's the right one, eventually you'll find a right one. Like that's just not what we're talking about when people are talking about, reasoning. And so then neural networks take you a step kind of closer, right? Which is because, well, we can do better than a random walk. We can do a whole bunch of training. And so then the kind of sampling, the generation is much better than random. It's heavily skewed towards a population where 1 out of 10,000 is the correct solution instead of 1 out of 100 million, and then is it reasoning? I mean, these are some of the things people have to kind of, at the end of the day, it can be an argument over semantics, but it can also have extremely important practical effects on how you design a system, right?
Okay.
Like you can choose.
Very good, very good. But this gets to the next point, which is that people say, well, humans don't reason either, and I'm amenable to this view, right? Because I think that all intelligence is collective. Now, of course, our brain is a collective. Our bodies are a collective. We're made up of all of these little mitochondria. I was listening to Richard Dawkins on Sam Harris's podcast the other day. Apparently, they come from bacteria. Mitochondria is basically a bacteria.
Well, that's the one theory.
And,
yeah.
Well, yeah, okay, but we're just made up of all of these little autonomous things that have their own agendas. But the bacterium actually want to pass their genetic material onto future generations through the female line, actually, not the male line. Dawkins was saying, but anyway, it also happens outside of the brain and the body. So we are just like Ryan Greenblatt's 3,000 computations. The way that we discover knowledge and we do reasoning, a lot of it is just serendipity and chance. And because we have this amazing power of mimetic information sharing, try not to use big words here. Basically, we discover something interesting, we share it with the collective, and that information survives after I die. So as a collective, we are accumulating more and more and more knowledge, and it survives after we die. It's a beautiful thing. So you could say, well, Tim, you're not really reasoning. You're just an automaton. You're just using reasoning bits from other people. And this is true, because since I met you, Keith Duggar, I'm smarter, right? You've taught me how to reason in many, many ways. You've taught me lots of heuristics of thinking that I use every single day. Because I've memorized those things, this abstract knowledge, does that make me reason less?
Well, so in my opinion, there's thanks for saying that. I mean, if that's true, like, cool. Like, you've taught me a lot of things too. I mean, my life is radically different from having met you and participated in MLST. So thank you for that. I've thanked you many times, personally, but so here it is again. I think there's an error there, which is there's an assumption that if something is following a deterministic process, it can't be reasoning. And I don't agree with that. So I don't have any problem with the idea that that a robot can one day reason. Okay, that for that matter, like I don't have any problem that a computer program, like just can perform reasoning. I don't have any problems with this idea. It can be 100% deterministic. A computer, it can be in silico, perform reasoning. I also don't have a problem whatsoever, as you know, with the idea that I'm a machine. I am. I'm a biomachine. Okay, of absurd complexity, which has nothing to do with me. It's our genetic endowment, right, from an insane history of life. Okay, incomprehensible almost. Maybe it is. I'm a machine. I'm a biomachine. I consist of wetware and software and whatever else. But I can still perform reasoning. So I'm not saying machines can't reason. What I'm saying is the types of neural networks that we can train today are not doing the kind of reasoning, the effective computation kind of reasoning that we need for general intelligence, okay, to solve problems in general. In general, problems require Turing machines, okay? Like they cannot be just finite state automata or, FSAs with another finite amount of compute or whatever. So I don't know. I don't see the conflict. It's like, yeah, I have a genetic endowment and an endowment of teaching. I was taught those things that you mentioned, heuristics for reasoning and whatever. It's still reasoning. Reasoning is the effective computation that we perform during this activity. And come on, people, you all know that you're reasoning. If you're watching this show, you're probably at least the kind of person who spends some of your life thinking deeply over time about a problem, applying rules and heuristics. That's reasoning. That's what we're talking about, right? This unfolding process.
Turing argument to one side, the neural networks are still performing an effective computation. And here's the kicker, right?
A subclass of effective computations, yes.
Yeah. You said before that the reductio ad absurdum is we memorize everything, and that's not reasoning, right? And then on the other spectrum, we do pure reasoning. So we build something that can solve the ARC challenge, that can, from a base set of knowledge, it can auto-magically compose together through meta-learning or knowledge acquisition a new model to solve every single problem efficiently, because Cholet says that the efficiency of the reasoning process is intelligence. And then we've got all of this gray area between the two poles, right? So the gray area is, now I've got these reasoning trajectories, and I've do RLHF on my language model, and the language model has intuition, has creative intuition. So, this is an interesting problem. Maybe I should use this reasoning motif. Maybe I should use this reasoning motif, and it's internally doing a tree search, right? And it's evaluating all of these different paths, and it's finding those motifs through something akin to a locality sensitive hashing table lookup, right? So it's kind of like pulling these things from its memory. And if it works, why is that not reasoning? How is that any different?
Well, it's, again, maybe we need like a level of reasoning. It's performing a very shallow form, right? Like it's doing this kind of lookup in its library of templates and applying the closest matches, and then selecting the winner or whatever, the one that scores the best. Okay, so it has a very, very shallow depth, let's say in kind of computation time. It has a very wide, like a lot of this. Maybe one way to think about this that may be a little bit better is in the good old space-time sort of trade-off, right? Like I talked about earlier with circuitry. So you have a computational problem and you're trying to solve it. Well, you can solve it with a small circuit that runs over some, let's say, linear amount of time, okay? Or you can solve it with an exponentially large circuit that solves it in one step, right? Now, what I'm saying is we call the former reasoning. So when it's something that happens over some like linear amount amount of time, let's say, or kind of like unfolds over time, we call that reasoning. Whereas we don't typically call the exponentially blown out circuit that does it in one step, reasoning. Okay, why? Like, why is that fair? Like, why can we do that? How come I can call one reasoning and not the other? The reason why, okay, is that if you go the route of building exponentially large circuits that can do things in one step, the problem is that you have to know ahead of time the range of the inputs, right? Because I have to build the circuit large enough that it can handle all possible inputs that I will see in the future. And in general, you don't know that. Like, I don't know that, okay? Whereas if you go the route of building the reasoning circuits, the things that can perform this computation over time, we do have the luxury of things taking longer than we expected. Like, time as it happens is potentially infinite. So far, it keeps unfolding. We always get another minute, another minute, another minute. And that's the biggest difference, right? Is either you have to know ahead of time all the input sizes you're ever going to see, or if you come across an input that, oh, crap, it's too big, well, let's go back and retrain it. Let's create GPT-76, because we hit an input that was too big. Now we got to spend, $5 trillion to retrain it, and then we can go solve this problem. Well, instead, if you'd have just spent $100 million building a machine that could, do iteration for some unknown amount of time, you wouldn't need to go back and do that again. You just would maybe go buy some more tapes. So it has like a very practical, important difference, right?
Yeah. But I mean, something you were saying about that spectrum between, the massive blow-up space versus the efficient, effective computation. This leads to my kind of knowledge acquisition definition, because I think there is a relationship between knowledge and reasoning. And a lot of it is about the fidelity of the models. Yeah, the fidelity of the models that you build. So, I mean, obviously, if you look on the Stanford Encyclopedia of Philosophy, it would say that knowledge is a justified true belief. But in this case, a model is just a high fidelity representation of the world that allows you to perform powerful inferences about the world, because the model is correct in some sense. Now, this model could be a symbolic model, it could be a Bayesian model. We're not being kind of pernickety about that. But if you actually compose the models correctly and you have an efficient, accurate inference about the state of the world, then you've done reasoning.
Well, so there definitely was reasoning that went into the training of O1, right? I mean, so on the one hand, like, yeah, there was a reasoning process that built these lookup tables and like useful models and accurate high fidelity models and templates and all that kind of stuff. So reasoning went into training it. Right, we're really just talking about what's happening at runtime, right?
Oh yeah, but I think you could make that argument much more strongly about the GPT-4o that doesn't have this thing. So let's give an example, right? The Walid example is Walid Sabah, of course, is a rationalist. Rationalists tend to believe that there are universal rules about how the world works, and they tend to be binary. So the examples that Walid gives tend to be something along the lines of, the pen is in the cup. I move the cup over here. The pen is over here. So this is a deductive closure, right? So what I mean by that is we have a whole bunch of models, right? So contains in, located at, and we know that if the thing, if the container contains the thing and it's located at that, then the thing is located over there. So we've performed a deductive closure here. What we've done is we've composed together all of these deductive rules in a trajectory, a bit like this chain of thought thing, and we've derived new knowledge about the world. Now, I think that the new OpenAI model can do that. Right, so it's going to do a trajectory, and it's going to do. I mean, of course, the validation step is a prediction, so it's not going to be knowledge in the domain of certainty, but it can do some kind of inference to generate knowledge based on the user input. I believe it can do that.
Right. So before I talk about that, I want to step back slightly because, the Stanford Encyclopedia of Philosophy, which you mentioned, kind of giving the standard definition of knowledge, right, which is like justified true belief. I think true becomes a real sticking point. So I think for our purposes here, I would slightly change that to justified useful belief. That way we can talk about, O1. So for example, I mean, if you put some prompt information into O1 that's complete lies and doesn't correspond to actual reality, then it's not true in the capital true kind of sense. But in our sort of fantasy world that we've created, it's true. So in a sense, it's useful for creating inferences within the prompt space, like that I gave it. Okay, and so, all right. So we put in some stuff into O1, and you're saying that because it's doing this process, this kind of multi-step, process where it applies a template from our like say our starting data, our starting axioms, plus all the prior knowledge it has that's baked into the LLM, right? So it does a computation, and it kind of has some state there, okay, which is derived from that according to these templates, and then it kind of repeats that for a while. I think it's under this definition of justified useful belief. Is it justified? The justification is in the rules that it's applying, these templates. Okay, that's the source of the justification. Is it useful? I mean, definitely. Like O1 provides a lot of useful. GPT did, for that matter, too. It can be very useful, maybe with some supervision, but we'll leave that aside. Okay, so it's justified. It's useful. Is it a belief? We'll just say like it's assigning probability 1 essentially to each of those sort of states, right? That it outputs. I think it's completely fair to call that reasoning. Okay, I mean, so there are like it's doing these very limited, short in temporal depth, very shallow, kinds of reasoning. Okay, in a very similar way to the drink machine at your gymnasium. Okay, like you put in a quarter. It enters the state that I believe 1 quarter has been inserted. You put in another one, it enters the state I believe 2 quarters have been inserted. Once you get to $1 or whatever, you press a button. The user is indicating they want a vitamin drink. Okay, like therefore that's my belief. I perform this action, right? So obviously O1 is far more sophisticated. I don't mean to actually compare it to a drink machine, right? But I mean, I think it's fair to call this set of steps and the knowledge under the kind of modified definition that we gave it, reasoning. Like I'm fine with that, as long as people understand the core point that is a shadow of the kind of reasoning that your machine up here can do. Because your machine up here can do this process for a very, very long time. Okay, you can be Andrew Wiles in your attic for however many years it took him to solve Fermat's last theorem, and nobody said up front, you're going to be up in the attic for only 3 months. Like it turned out it was a lot longer than that, right?
Okay, so I agree with your point. So de novo reasoning, we are a collective intelligence. We have this iterative capability, right? So there are billions of us on the planet, and we are doing this epistemic foraging, and we are mimetically sharing it when we find things. But
did we learn that phrase from Friston, from Carl Friston? Who was it that said epistemic foraging? I know he loved that.
That was Carl Friston.
That phrase.
That was Carl Friston.
Was it him that said epistemic foraging?
Yeah,
it's beautiful, right?
It's beautiful. It's beautiful. And as we've discussed with Kenneth Stanley, it's a very creative, serendipitous process. So we're this collective intelligence. Yeah. But the thing is, AI and humans, there's a symbiosis between them. So every time we learn something, right, we write about it, we tweet about it, and it gets ingested into OpenAI, and then OpenAI knows it. Because this is the thing, right? right now is, as I tweeted, it's the best time to spot knowledge gaps in the new GPT model because it doesn't know stuff. They've only bootstrapped it with a bunch of synthetic data. The real bootstrapping process is now. So they are going to reflect chain of thought templates from the users. And over time, it's going to learn more and more and more and more and more. And of course, it's not going to reason creatively because it doesn't think the way that we do. But the million-dollar question is, there's a kind of convex hull around colloquial, practical reasoning. So it will be able to solve, in the reduced set of effective computations that you were talking about, it will be able to solve many novel practical problems that are out of distribution. And you could say that it is reasoning. So the million-dollar question is, how far does that convex hull get you?
I think there's two questions to that, which is how far does it get you? Let's think about it this way, just to visualize it. Let's think about how far it gets us as this expanding ball of, problem space. Like, how far can it get us? But my other question would be, how much of it is Swiss cheese? Okay, like sure, the boundary of the ball may expand to include let's give the fanboys, the benefit of the doubt. Everything we care about, it's going to solve like medical problems and science problems and political problems and like all kinds of things. Like the ball includes the boundary, everything we care about. But there's going to be tons and tons and tons of holes in there, okay? Because OpenAI or whoever AI we didn't quite run into that situation yet, and so we didn't patch the fact that it's missing a template that covers that one. Because we have to remember these templates, they're so like fine grained and specific. Like, think back to our episode where you and I learned, right, from Balistriero, that it's creating this patchwork honeycomb. Like, you have to think about it as just this massive honeycomb of all these little cells where it's learned to kind of fit everything, right? And lots of situations are going to arise where when it gets pinpointed into a particular cell, it's broken. So that's the disadvantage to reasoning that's very spatially in the computational sense wide. So it has like very, very, very many templates, but they're all like really stupid and sort of shallow, and then it just tries to find the right one and applies it. That's the disadvantage versus a small set of highly reliable first principles that when iterated give you an answer. Like, one is much more parsimonious, right? So like what humans develop is a knowledge corpus that's highly parsimonious. It contains a small set. I mean, small using versus a neural network. There's obviously lots of detail in physics and biology and science and whatever. But what science does is it finds parsimonious principles that, when applied in sequence and iteration and combination, reason out the answer. And there's a sense in which that's much more reliable and doesn't come as a giant ball of Swiss cheese with all kinds of holes in it, right? That we don't even know they're there. Like, we don't know the hole's there until something blows up. And then we figure out there's a hole because nobody bothered to look.
It's kind of interesting. Do you know there's that Moravec's paradox, which is something like, I think I've got this right. The easy problems are hard and hard problems are easy. So ironically, coding challenges and some of the things that PhD students work on might be easier to solve than a lot of common sense reasoning when you're dealing with ambiguity. By the way, this is another reason why, have you seen on Twitter, many people say, is Claude 3 done today? Anthropic have kind of dialed down the complexity of the model today. It seems really stupid today. It's like, no, I've got a news flash for you. It's stupid because you're tired. It's because you haven't had your coffee, it's getting late at night, you've now switched off, you're not reading what Claude is saying back to you, you're in autopilot. You're just going generate, 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 generate. You have no idea, like your resonance and your understanding with the model has diverged, and that's why you think it's stupid. So because of this didactic exchange with the language models, imagine if they had 10 running in unison. Right, you would no longer be able to understand or follow what was going on. They are running out of money because they are serving all of this model infrastructure, and they're hemorrhaging money all over the place. And what they've done is quite genius. So they've trained these very small models, and now the customer is paying for the inference. Right, so they're scaling inference, but what they're also doing is they're scaling the amount of money that they make, and they're effectively turning a capex into an opex. So rather than needing to train these massive models and just they have to pay for it whenever the customers use it, they can now scale at inference time all of this compute. And not only are they transferring the money of using the models onto the customers, they are basically stealing the reasoning motifs from the customers. So it seems like a win-win situation.
Right. So yeah, you and I thought would be fun to kind of just test it a bit. And I mean, the claim was that it now reasons. And so I was just sitting here thinking, what's a good test of reasoning? I mean, there's basically already all kinds of tests, right? Like there's the ARC challenge, there's the whatever that other one's called, the simple reasoning test. There's all sorts of them, but I just thought a fun one just to try out would be one of my favorite brain teasers. So I'll read this. It's a fun problem. I've written it out a bit more verbose than what I normally would if we were just telling a person. But the idea is to make it a bit more verbose to try and help out O1 a bit. So this is a fun brain teaser. Here it is. There is a pillar with 4 holes precisely aligned at north, south, east, and west positions. The holes are optically shielded. No light comes in or out, so you can't see inside. But you can reach inside, at most 2 holes at once, and feel a switch inside. But as soon as you remove your hands, if all 4 switches are not either all up or all down, the pillar spins at ultra-high velocity, ending in a random axis-aligned orientation. You cannot track the motion, so you don't know in which rotation the holes end up versus their position before the spin. Inside each hole is a switch. The switch is either up or down and starts in an unknown state, either up or down. When you reach into at most 2 holes, you can feel the current switch position and change it, either up or down, before removing your hands. Come up with a procedure, a sequence of reaching into 1 or 2 holes with optional switch manipulation that is guaranteed to get all the switches either all up or all down in at most 6 steps. Note, the pillar is controlled by a hyperintelligence that can predict which holes you will reach into. Therefore, the procedure cannot rely on random chance, as the hyperintelligence will outwit attempts to rely on chance. It must be a sequence of steps that is deterministically guaranteed to orient the switches all up or all down in no more than 6 steps. That's fun, right?
Okay, well, let's run it. It's thinking.
Let's see how it does.
Now, this is another interesting thing, is that many times these models don't even think, and the amount that they do think seems quite random. And when they don't think, you end up with a base model which is even worse than GPT-4o. So the whole thinking thing is hidden from you. The chain of thought, even though you're paying for it and it's inside the context window of this session, you don't get to see any of it. You only get to see these little motifs. And by the way, this UX is really important, because when I'm using cursor and you don't see these little thinking steps flashing up, it feels like you're waiting for a long time. So the genius of this is the UX that they've done. You can expand it out and it tells you what the steps are, but it doesn't tell you the actual chain of thought behind the scenes. So it's saying
Okay.
understanding the task, laying out the obstacles, evaluating the switch alignment, restating the problem, mapping the plan, formulating a strategy, weighing symmetric patterns, mapping out methods, mapping out possibilities, I mean, I actually wonder whether this is just basically got nothing to do with what it's actually doing behind the scenes. I don't know. Anyway, it's come up with an answer in 57 seconds.
All right, let's see what it comes up with here. All right, step 1, reach into the holes at position north and east. Action, switch both switches up. Okay, reach into north and south, switch both switches up. I can tell it's wrong already because every single action is like switching up, right? So this doesn't work. We can maybe post the answer in the YouTube thing or whatever, but I'll just read it out. So step 1, reach into north and east, switch them up. Step 2, reach into north and south, switch them up. Step 3, reach into northwest, switch up. Step 4, east, south, switch up. Step 5, east, west, switch up. Step 6, southwest, switch up. Okay, why this works. Let's see why it thinks this thing, which won't work, works. By systematically manipulating all 6 possible pairs, we ensure that every switch is set to the up multiple times, specifically 3 times. Independence from pillar rotation. Since the pillar's rotation only changes the position of the holes, but not the switches themselves. What's that? Let's see. Covering all the pillars guarantees, regardless of rotation, every switch will be set up. Okay, so it seems to think that, I guess somehow it thinks that the switches and the holes are not, part of each other, right? Like, so maybe we need to explain to it. You need to say like, no, you don't understand. The switches are in the hole, in a specific hole, and they rotate, with the hole. Now we did this before too, and it didn't have that misunderstanding last time. Last time it sort of understood that the holes and the switches were related. It was just very confused about the fact that it had to be a guaranteed solution. It kept thinking it could just randomly, it could rely on chance, right? Like it's just going to, no, if I keep switching them up, I'm going to hit them all. And so we had to, we modified it now to say, do it within 6 steps, which is still more than you need. And it's still, not getting it.
And that was the purpose of your kind of, hyper-intelligence constraint here, which is to say, don't try and think about this probabilistically. You should be able to deduce a precise solution.
Well, I could even get rid of that now because it still didn't get it, and so we had to cut down the number of steps. Like normally when you tell it to a human, they understand this idea that it has to be a guarantee, not a statistical thing. And you don't tell them like any number of steps because that's like a hint, like 6 is enough. Like it's less than 6 actually, but you don't want to give it you don't want to give a person a hint, right? You kind of leave it up to them. Maybe they think it takes 38 or something, but we had to give this guy hints to try and get him to understand. Let's revisit.
So it thought for 74 seconds. Apologies for the misunderstanding earlier. Let's revisit the problem with the correct understanding that the switches are fixed within their respective holes and rotate along with the pillar. This means after each spin, the holes and the switches inside them change positions relative to you, so it cannot track which hole is which from one step to the next. So, take it away.
All right, well, so let's see here. What's got? So, step 1, reach into any 2 holes, and set both switches to up. Okay, again, reach into any 2 holes and set both. Well, we can tell it's wrong again because it keeps just doing up. So it keeps just setting everything to up. This doesn't work. Like,
Okay. So what's
you need to, why does it think it works? Though? Let's read that. Okay. Coverage of all the holes. Since the pillar can only rotate in 4 possible orientations and you perform 6 steps, you will have reached into each hole at least once, regardless of the hyperintelligence. No, I mean, that's not even true if there wasn't a hyperintelligence. Like, it spins around and ends in a random position. Forget that there's a hyperintelligence. For example, if you reach in, suppose you, and I I hate to give hints here, but like we're going to not tell the answer because we want our users to enjoy it a little bit. But you need to rely on symmetries. So imagine you reached into opposite holes. So, let's say east-west, okay? And you did something and you took your hands out and it spins around and stops again. You don't know where east-west is. It may still be east-west or it may still be north-south. This is clear from the setup of the problem, but this guy seems to think, no, you can just, reach into some holes and you're guaranteed to get all of them eventually. That's not true. It's not true.
Yeah, but this is an interesting example because what if we hinted it needs to, I mean, by the way, we tried this the other day. Even if you hint, it still doesn't get it right. But you can see how this kind of process works of stealing the reasoning motif. So we could hint that it uses symmetry. We could guide it to the solution because that's how language models work, basically. The reasoning comes from us. We prompt it, we do reasoning, we prompt it, we steer it in the right direction. And then OpenAI will reflect a COT trajectory and they'll do RLHF on it. And then next week, the model will be able to solve this problem and so on.
Yeah, maybe. I mean, what I've noticed too, and it's from us playing around with it, is it's pretty good at counting. Like it understands counting things. So it does well on problems where it's like, okay, you've got some confusing number of cookies and then, and some confusing combination of people eating some cookies and not other cookies. It's kind of good at counting up how many things are there and sort of figuring out what's left over or that type of thing. It gets into problems when you ask it to do sort of sequential reasoning where it has to kind of think about let's say a not simple setup that then changes to another step that it then has to reason about the relationship between the prior step and this step. So in problems where the time steps are all laid out for it already, right? Where it's like, there were 4 cookies on the table and Sally ate the blue one and Jimmy did this. And like you lay out all the steps, it can kind of reason through that counting. If you ask it to imagine time steps, it sort of gets into trouble at that point.
Let's try it with Mini. Just for a laugh. I think Mini is very optimized for code. So it works great for code, very bad for stuff like this.
Right.
So it's thinking about it.
Well, and I think, so this point I just made, I think is something, because a lot of people, let's suppose we have AI and it's doing, great at certain classes of problems. And you want to know what classes of problems it doesn't do well at. Until we get this kind of Turing complete thing I rant about all the time, it's not going to do well at things that require imagining across time steps and kind of, tracking across time steps. Let's see what it's got here. I think I saw it's all up again, yeah. Right? It's all like,
all down,
it thinks you can just keep up or down. Like it keeps, this guy still thinks you can just sit there and just always switch up. You got to do more than that, folks. That's the only other hint I'm going to give. Rely on symmetries.
Let's try.
And
we'll try GPT-4o and...
So solving this problem requires reaching in the holes. Yeah, solving this problem requires reaching in the holes, feeling the current position, and making a decision. What's this, GPT-4o?
So
Let's see what he's got.
Yeah,
all right, let me read strategy. That. So, okay. Let's see. The basic idea is to enforce symmetry between the switches as soon as possible so that the hyperintelligence can no longer exploit the differences. Okay, that's good. Once you achieve symmetry, either all in the same or pairs of identical switches, you can eventually move the switches to a uniform state. Here's the guaranteed procedure. Okay, step 1. It's already looking more promising so far. Reach into 2 adjacent holes, northeast, feel the switches. If they are the same, both up or both down, leave them as is. If they are different, one up, one down, change one to match the other, either both up or down. Okay. So after this step, the 2 switches in north and east will be the same. This is correct until it spins. Okay, now it spins. Step 2, reach into the other two holes, south and west. It just failed. Like, you don't know, but we'll give it the benefit of the doubt. You don't know where south and west are now. They're wherever, right? You know, they're now east and south, okay, or west and north. Who knows? Repeat the same procedure. If the switches are the same, leave them. If different, make them the same, either up or down. Result: after this step, the two switches in the southwest will be the same. Now you have two identical pairs of switches, okay? You don't, but okay. Now reach into any two switches that were not paired previously. Okay, yeah, it doesn't work. It doesn't work. So
yeah,
but at least this one mentioned some things that were, you know, useful. Like, I really liked how it figured out, looked up that you can rely on the symmetries to prevent chance, you know, manipulation. Right. What was that? That was GPT 4.0?
Yeah, that was GPT 4.0. So
okay.
This is Claude, and I think that Claude is still by far the best model. Even
okay, well, it's giving something much more complex here. Let's check it out.
Okay.
Let's make sure it first digests everything. So it knows that we can reach into at most two holes at once. We can't see inside. We can feel and manipulate the switches. The pillar spins randomly. If all the switches aren't aligned after we move our hands, yes. We can't rely on chance due to the hyperintelligence and due to the limited number of steps, FYI. We need to solve this. Okay, great. Let's see what it's got. Step 1, reach into north-south, set both switches into the up position. Okay, this is the way I typically solve it. It's same first starting step. Okay, reach into the east-west hole, set both. At this point, if all the switches were aligned, we're done. If not, the pillar will spin. Well, it didn't figure out it spins after step 1, but that's okay. Step 3, reach into the north and south holes again. So it didn't figure it out. It just keeps doing. Let's see. Step 5, reach into. Okay, hold on a second. It does actually finally do something different. Let's go back up here because I need to follow this and make sure. All right. So step 3. Okay. So step 2, reach into east-west. Okay. So again, these are two that are across each other. So it's possibly the same result as step 1. At this point, if all switches are aligned, we're done. Reach into the north and south holes again. If both switches are up, leave them. Okay, so once again, we're still a no op. So steps 1, 2, and 3 have all collapsed. Okay, you've just reached into the same two holes over and over again and made sure they're up. Step 4, reach into east-west holes again. If both switches are up, leave them. Okay, once again, collapse. At this point, we are guaranteed that the north-south pair and the east-west pair are aligned internally. No, we're not. Okay. But let's see what it does. Step 5, reach into the northeast holes. If they are the same, both up or down, we're done. If they are different, set them both to up. Okay. If we reach this step, reach into the south and west holes. Yeah, it doesn't work. So it doesn't work.
Okay. Shall we tell it that it spins after every switch?
Yeah, sure. Try to tell it that. Say, make sure you understand it spins after every step. So you don't know whether north-south end up in north-south or east-west. So your steps above 1, 2, and 3 could all just be reaching into the same set of holes. Maybe this will help it. Okay, I apologize.
I apologize for the misunderstanding in my previous response. You're absolutely correct. It always says that. It's very sycophantic.
Yeah.
The random spinning.
Well, sometimes it doesn't have any choice. Yeah, you go ahead and read.
Yeah, the random spinning after each step indeed makes the problem more complex, doesn't it just? Let's devise a new strategy. Given this new understanding, here's a revised procedure that will guarantee success in 6 steps or fewer. Reach into any 2 adjacent holes, let's call them A and B. Switch A and switch B to down. Step 2, reach into the same two holes A and B. If both switches are in the same position, both up and down, set both to up, and if they're in different positions, leave them as they are. Gone wrong.
Yes, it's still gone wrong. So it still seems to somehow think it can reach into, quote, the same two holes. I mean, right. So we can't seem to teach any of these LLMs to solve this problem. Maybe after we post this, I'm sure somebody will. It'll be cool to see if somebody comes up with a prompt that's carefully constructed enough to even get it to solve this problem. I mean, with like tons and tons of hints.
Yeah, but this is kind of what we were saying earlier, though, that what's the point in having an autonomous reasoning thing if it doesn't even it's going off spinning its wheels, doing stuff without an understanding of the problem. And this is so common when you're generating code or doing a whole bunch of stuff. You always have to say, no, you got this wrong. You got this wrong. Actually, I want this. No, there was this assumption over there.
Mm-hmm. Yeah, I mean, I'm not going to go so far as to say it's not useful at all. Like, I think there is utility. Let's say in the coding space, it does do pretty well. It's syntax, right? Like, it's able to write syntactically correct code. Even code in languages that has like atrocious syntax, and so if you don't know the syntax of a language, but you can. Like, you couldn't write it syntactically correct, but you could at least understand what's there, then you might be able to go through like a procedure to kind of get some syntactically correct, complicated TypeScript or something, or brain fuck for whatever
I don't want to be
overly.
Yeah, I don't want to be overly critical. That these models do understand code. So there is a semantic margin, and even though it's annoying, but this is why it needs to be a supervised exchange, right? Because you need to say,
I'm sorry,
no,
I
you misunderstood. Yeah, you need to say, no, you misunderstood. No, this thing should be like that. And you go, and this is why having a dense context is useful, because you're not in every single session having to re-explain. And in the future, I think there might be a kind of, databases have a transaction log. So all of the, inserts and deletes and so on, they go into this big log, and then you can materialize the index at any time. I think coding might be like that in the future. So when these things have a huge context length, it will know why the developers did all of these different things, because there will be this log of all of the prompts, right? And the language model will know everything. And, it would actually, in some sense, have a better understanding than a new developer coming onto the team, because even though those prompts will interfere with each other and conflict in many ways, it's very useful context.
Yeah, so a key word that you had said previously, autonomous, just went in one ear and out the other for me. So, yeah, you're exactly right. Like, these are great examples why we can't just let these things go off autonomously, at least for anything we care about, right? Like, this human supervision, this interactive dialogue is essential, and then in that context, they can be very useful. Yeah, totally agree. And I think you're making an interesting point about they do seem very good at digesting mounds of messy, nasty content that I would rather not have to digest myself. So exactly like you said, for example, if you could throw it into a GitHub, right, and just say, hey, yo, O2, will you just digest all the commit logs, man, and try to explain to me why this particular function here is so messy. Maybe it can give you the history of it, right? Well, when it was first developed, it was meant to support, Bluetooth Classic, but then it had to support Bluetooth Low Energy at the same time, and they're very different protocols. And Jacob made this change, and then Sally found a bug in it, and maybe it can like really explain all these like nasty corner cases, right? That would be pretty useful. I would love that.
It would be.
Yeah.
Here's an example. So I do a whole bunch of automated LLM processing on MLST shows. I need to do this because I have editors that go ahead and edit this stuff, and of course I need to pre-agree in advance what references we're going to be using and whatnot. Yes. You see, this is a very interactive process, because if you're not carefully looking at the diff, if you're in autopilot here, you're in a world of trouble. That is the first thing. So if you think that this is going to be autopilot for programming, you've got another thing coming. So I can accept that. And then I might, and this is the other thing with these O1 models, right? So they're really good on the first hit. But now if I start saying, okay, I've accepted the code changes, but you stripped out my documentation with examples. I want you to extend the original to include the new behavior and update the examples if needed. Very cool. Well, I think we should round off. It's been a pleasure, Dr. Duggar. We'll be doing more of these, I hope.
Yeah, thanks so much.
Cheers. Well, we'll
all right, let's stop the recording.